What is migrated during the vMotion? Well, when we vMotion a VM, we move the VM from source host to destination host. But VM has a lot of states associated with it. VM has virtual processor, virtual devices, it has an association with physical network and VM decays. So the vMotion process somehow has to move the VM state from source ESXi host to destination ESXi host. So the majority of these devices movement is handled by something called checkpoint infrastructure, which is built into the ESXi and used by other features, inputting suspend resume. The idea is that this process organizes all of the VM's virtual devices and serialize their state into a checkpoint opaque blob and send them from source host to destination host, and then deserialize the state at the destination VM and end up with same virtual device state at the destination as it has at the source. But that is not that simple because the VM has an association with the physical resources. For example, the physical network, the VM decays. So vMotion process also need to migrate these associations. In case of storage, the vMotion process requires that source and destination VM must share all the common storage used by the VM's VM decay. In other words, whatever storage that VM is relying upon needs to be accessible by both source and destination host. What vMotion process does is releases the ownership of that VM decays on source host and open the same VM decay on the destination host, and the storage transfer is done. Similarly, for the physical network, after the VM state is transferred to the destination host, the host sends a reverse ARP request to the switch, and the switch updates the destination VM's MAC address. Now, the most important part that takes place in vMotion is migrating VM's memory. VM's memory is transferred from the source to destination ESXi host via pre-copy convergence by using multiple iterations. The first iteration, pre-copy phase 0, copies the virtual machine's memory. The following iterations, pre-copy phase 1 to n, works on copying the dirty memory pages. To give you an example, this is what the iterations could look like as you live migrate a virtual machine with 40 GB of memory. Phase 0 copies the 40 GB of virtual machine's memory and trace pages. As the process sends the memory, it dirties 10 GB memory again. In phase 1, the pre-copy retransmits the dirtied 10 GB pages again, and while transmitting these pages, the memory dirties again 3 GB. In phase 2, the process sends the 3 GB. While the transfer is happening, the virtual machine dirties again 1 GB. In phase 3, the process sends the remaining 1 GB. As the memory pages are copied from the source to destination ESXi host, VMM asks the VM kernel if the pre-copy process can be terminated after each iteration. This is only possible when all memory changes or dirty pages are copied to the destination host. Part of the iterative memory pre-copy algorithm is to match all the destination memory pages to its source, starting at page 0 all the way to the maximum or last memory page number. All memory pages are subsequently checked to see if the destination pages are in sync with the source pages. To determine if the process can terminate pre-copy, the process needs to verify whether it can complete the last memory page copied in a window of less than 500 milliseconds. If no, the next iteration happens. If the outcome is yes, the VM kernel migrate module will terminate the pre-copy process. Now, what will happen if the dirty page rate is higher than the migration transmit rate? If that is the case, there is no point in doing another iteration because the process can never reach memory pre-copy conversions and the migration would come to a halt. This is why VMware introduced Stun During Page Send (SDPS) with vSphere 5.0. Basically, SDPS is a way for the VM kernel to tell VMM to not run the schedule instruction, but to introduce a really short sleep. This may sound like impact on workload performance, but this happens at a fine-grained level. HDPS is executed with each iteration if the dirty page rate is greater than transmit rate. Subsequent iteration only copy the dirty memory pages that were modified during the previous iteration. A shorter duration in iteration gives the guest OS less opportunity to modify or dirty its memory pages, thereby shortening the next pre-copy iteration. With the memory pre-copy migration transmitted by VMM, all memory pages resides on the destination ESXi host. VMM sends a remote procedure called RPC to VMX that it can suspend the source virtual machine. VMX will enter the checkpoint phase where it suspends the virtual machines and send the checkpoint data to the destination ESXi host. In the process, the virtual machine on the destination ESXi host will be demasked and state is restored using the checkpoint data.